Hello, Math 30-1s. So we're looking at lesson 8.2, transformations of logarithmic functions. So a recap from 8.1 is an earthquake intensity is given by this equation, where I0 is the reference intensity and M is the magnitude. An earthquake measures 5.3 on the Richter scale, is 125 times more intense than a second earthquake. Determine the nearest tenth the Richter scale measure of the second earthquake. Well, what I want to do is first write it as a comparison. So I want to write it as, we want to find out the amplitude of one earthquake, and then we'll compare it to the other. So we know that I over I0 is equal to 10 to the power of m. So we know that one earthquake is equal to 10 to the power of 5.3 if we were to compare them. And another earthquake is going to be 10 to the power of some unknown. We can call it x. So we know that this 5.3 is 125 times more intense, so it's stronger than the other one. So whenever we're comparing earthquakes, we're going to go 10 to the power of the higher number divided by 10 to the power of the lower one, which we don't actually know. And we know that the difference between them, meaning the division of them, is going to give me 125. So what we're going to do is simplify this. Whenever you divide common bases, you're going to go 10 to the power of 5.3, subtract the bottom power, and that equals 125. Now this is where we can change this to log form. So log is always the base 10, so that's that little number that, so this is our base of our answer, 125, is equal to our power, 5.3 minus x. So this comes from our formula sheet, converting between our exponential form and our log form. So all we have to do is put this into our calculator, the log base 10 of 125. So we can just go log 125 because you don't have to write the base of 10. And so we'll get 2.0969 equals 5.3 minus x. And now what I'm going to do is I'm going to swap these numbers and their spots because I want always x to be positive, and I'm going to move that 2.0969 to the other side as well. So I'm going to get x equals 5.3 subtract 2.0969. So in my calculator, I get 3.2. So we do want the answer to the nearest tenth, so I know that the Richter scale value is going to be 3.2. Now, in this lesson, we're just comparing and looking at the graphs of these logarithmic functions after they've gone through transformations. So in this case, our x is being affected by this minus 10, which means that there is a horizontal translation. A horizontal translation of 10 units to the right. And we also know that there is a vertical translation of 1 unit down. Okay, so I'm just doing abbreviations just to show you. And then what you want to do is draw this. So we're actually going to use our graphing calculator to draw what this looks like. But you should see that the log function that normally looks something like this is going to now move 10 units to the right and 1 unit down. Okay, so that's going to actually affect our vertical asymptote. Normally our vertical asymptote is where x equals 0, and what you're going to see is that it's going to shift to x equals positive 10. So that's kind of like the biggest thing that we should notice. Okay, so in your graphing calculators, you should be trying to graph this function, clear whatever you have there right now. So we have log in brackets x minus 10, and then we have subtract 1. Our standard window, we might have to adjust it slightly to go a little bit bigger. So I'm going to go from -10 to, let's try going up to 100, because I just want to show you that it's going to extend. Since we know that the whole graph shifting 10 units to the right, I just want to show you what that's going to look like. The y is just going 1 down, so that's not really going to affect it, so we can leave it as the standard y value. But once I graph it, you'll see something like this. What you want to really notice is that this right here, even though it looks like it stops at that point, it does go down forever. So that's something you need to realize about your graphing calculators, is that the accuracy is not really there, so you need to extend the graph and know that it does extend forever downwards. Okay, so that's important when you draw it, is that don't draw exactly what you see, draw what should be happening. Okay, so when I go back, I should have a vertical asymptote. So I'm going to go up by 10s just to show you. So this will be 10, 20, 30, 40, 50, all the way to 100. This is our x's. Our y's will stay the same. Okay, just to get a little glimpse of what you should be looking at, we want to draw this dotted line at 10, because there's our vertical asymptote, the line that it's going to approach but not touch or go through in this case. We do want to find out, in this case, what the 0 is. So if you go to the left side of that x-intercept, the right side of that x-intercept, you should find that the 0 is at 20. So there's an x-intercept right there at 20. And then we're just going to draw our graph going through that 20 and then going as close to that dotted line as possible without going through it. So we can always go to the table of values to get a better image of it, if need be. And then just again, just going the other way. Okay, so something like that. Okay, so the equation of the asymptote, we have a horizontal asymptote, actually a vertical asymptote, because it's a vertical line, at x equals positive 10. So for I, I'm going to do that over here. The domain now is going to be rounded bracket from 10 up to positive infinity. So you'll notice that it's not a square bracket because I shouldn't touch 10 because that's a vertical asymptote. Our range should go from negative infinity to positive infinity. So it does go forever up and down. For 3, our y-intercept does not exist. We're going to say none. And our x-intercept we already found should have been when x equals 20. Okay, so that's kind of what we're doing in this lesson, is we're looking at the transformations and seeing how it affects our features. So as you can see, that horizontal translation of 10 units to the right affected our domain, and it affected that vertical asymptote. So those are important things to note. Now, since our range was going from negative infinity to positive infinity, that vertical translation didn't affect that. Example number 2. So in your calculators, since we have this base of 2, you're going to have to, in the you're going to have to watch how you put that in your calculator. So if you have a newer version calculator, you're going to have to press alpha window number 5 in order to place that in. If you have an older version calculator, the TI-83s, you're going to have to go y equals 2. You're going to have to do log of what's in the brackets divided by log of 3. So that's the older style calculator. So these are 2 different ways to actually do that, right? So whatever version you have, make sure you practice. Okay, So going to your graphing calculator, let's sketch what this looks like. But we also want to talk about the transformations that are occurring. So here we have a vertical stretch about the x-axis by a factor of 2. Also, we want to rewrite this because 2 log base 3, we're going to have to factor out the negative. So that's always an important thing, is factor out whatever's in front of x if you really want the correct answer. So we also have a reflection about the y-axis. And we are going 1 unit to the right. 1 unit right. So that's our horizontal translation. Okay, so that's why we had to factor the negative for us to see that it was going to the right and not to the left. So if we didn't factor it out, we would probably make a mistake there. Okay, so in your graphing calculators, you should be graphing this. Now I'm going to just do it in this one. I find the other one is a struggle. Okay, so I'm just putting it into my calculator, and I'll tell you what you should be seeing. So just write it exactly how you guys see it right there. Just make sure you know if you have the older version or the newer calculator, and that will help you draw it correctly. Okay, so what I'm using is the standard window, guys. I'm using the 1, 2, 3, 4 all the way to 10. 1, 2, 3, 4 all the way to 10, -1, etc. Okay, so once you have that, so what we want to do is we want to find out what our x-intercept is by doing 0, second trace 0, going to the left side of that x-intercept, the right side of the x-intercept, and you should find that the coordinates are really at 0, 0. So you should find that your graph actually goes through 0, 0 right here. I'm going to use a different color, so there's my value here. Another thing that's important is that we have a vertical asymptote at 1. Because of this value right here, our graph, our horizontal asymptote moved 1 unit to the right. So our vertical asymptote usually is at x equals 0, but now it's at x equals 1. And now instead of the graph being on the right side of that vertical asymptote, which it normally is, we're on the left side because there's been a reflection along the y-axis. So we're going to draw a graph on the other side of that. So that's something that we need to state and show. So I'm just using some coordinates to graph a little bit of it. So I looked at the table of values by going second graph, and you should find that there's a point at -2 and +2. So there's a coordinate right there. There's a coordinate at 0, 0, which we already plotted. And we have a coordinate at -8 and 4. So -8 and +4 would be right here, and that gives us a good picture because now we can connect these points and then draw it very close to that red asymptote line without touching it. Okay, so that's what our picture should look like. Now from there, I'm going to state the equation of the asymptote. So we're going to have that vertical asymptote just like previously. Use that horizontal translation to help you for that. It's going to be at x equals +1. The domain is now going to go from rounded bracket -infinity up to +1 rounded bracket. Range is going to go from -infinity to +infinity because it goes forever upwards and downwards, so that's not being affected by any of the stuff we just did. Our y-intercept actually exists. It's going to be at y equals 0, and our x-intercept also exists at x equals 0. So we have both in this case. Okay, so that's example number 2. Okay, so it said a red graph can be generated by stretching and reflecting the graph of y equals log base 4 of x. Write the equation that describes the red graph. So we want to figure out what happened. Well, first of all, we can see that there's a reflection clearly, right? So there's a reflection along the x-axis. So we've been flipping the graph across this line right here, so we can write that. Reflection about the x-axis. Now let's see what's happening with the coordinates. We always want to compare points and see how they've been affected. So looking at these 2 circled points, let's write them down. So we know that the original one was 4 and 1. And what it became was 4 and -3. So we already know that there's a reflection about the x-axis, which means our y-coordinates become the opposite. So that's clear because our 1 would have become -1. Now, what happened to take us from this to this number? Well, we're multiplying by 3. Our y's are multiplying by 3. And because of that, we know that there is a vertical stretch by a factor of 3. About the x-axis by a factor of 3. Good. And now we just need to write the equation down. Well, we're going to write y equals, the reflection about the x-axis will be negative, and then the 3 will represent the vertical stretch, and everything is the same. Everything else stays the same because there's been no kind of horizontal stretches or translations. So that is our final equation that matches it. Now you can always graph this to check that it does look like the new red graph. Example number 4. There is a logarithmic relationship between butterflies and flowers. In one study, scientists found that the relationship between the number f of flower species that a butterfly feeds on and the number b of butterflies observed can be modeled by this function. So they're giving us an equation that represents all of this. Predict the number of butterfly observations in a region with 25 flower species. So what we're doing is we're replacing our f, our flower species, with 25. So we're going to have 25 equals negative 2.641 plus 8.958 log of b. So we can do this algebraically. We can start by adding 2.641 to both sides. And then in my calculator, I'm just going to write this in and start doing the math. 25 add 2.641, 27.641 equals 8.958 log of b. Now we're going to divide both sides by 8.958. (27.641) divided by 8.958, we get 3.086. So I'll write that log b. I'll round it to, actually I'll keep a few decimal places just for more accuracy. And then we can change it into exponential form. So remember, the base, if you don't see it, is a 10. So we're going to write 10 to the power of, our power is going to be the answer, which is 3.08562, and that's equal to b. So that's what we're putting into our calculator, 10 to the power of 3.08562. So we get in this case that b is approximately equal to 1217, so 1217.9. Now, number of species should be in whole numbers, so we're going to round to 218. So I'm going to round this to 218. So b is equal to, let's do the approximation symbol, to 1218. And we will say this is the butterflies observed. Done. Example number 5. The graph of y equals 3, in brackets, the base is 7 to the power of 2x minus 1 plus 5, is reflected in the line y equals x. What is the equation of the transformed image? Well, we want to do the inverse. So we want to solve this by doing the inverse. Once we do the inverse, we can then get our answer. So first of all, we're going to bring that 5 to the other side, but we're going to swap the x with the y. So we're going to become, so it's going to become x equals, so that's step 1, is swapping the x with the y. But instead of x, let's write a y. There you go. And then we're going to move that 5 over, so it's going to become x minus 5 equals 3, bracket 7 to y minus 1. Then we're going to divide both sides by 3. So that crosses off the 3's, and you're left with 7 to the power of 2y minus 1. Now we're going to change it to log form. So remember, we always write log of our base, which is 7, and becomes that small little number. In brackets, we put our answer, x minus 5 over 3, and that equals our power, 2y minus 1. So we're almost done. Now we just have to isolate for y. So we have to bring that 1 to the other side. So it becomes log base 7 of x minus 5 over 3, and that is adding 1 equals now 2y. And now we're going to divide everything by 2 by just putting a 1/2 in front. So that makes it a little bit cleaner looking if we just do 1/2 in front instead of dividing everything by 2. It still means the same thing. And then we also need to, this 1/2 affects everything. So if we really want to distribute it, we can. So we should say 1/2 log of base 7. And then x minus 5 over 3. And then if I distribute that 1/2 to the 1, it becomes positive or plus 1/2, which is equal to y. And then lastly, they want us to do the inverse again, but we know now it's a function. So this just means that our inverse is going to be a function. So that's the notation that that shows us that. So it's very similar. In this case, start by swapping the f of x with x, and the x becomes y. Okay, we're going to move the 8 to the other side. X minus 8 equals 2 log base 3 of y minus 1. Divide both sides by 2. Now we're going to change it to exponential form because it's already in log form. You're just trying to go to the opposite form. So it's always going to be that little number is your base. So it's going to be 3 to the power of your answer, in brackets, equals what's after your little base, which is y minus 1. There you go. Technical difficulties. Okay. And y minus 1. And now we're just going to move that minus 1 to the other side. So we have 3. What we can do is write it as 1/2 if you want, x minus 8. The reason we can write it like that is then we can see that horizontal stretch. It becomes more clear if you write that dividing by 2 as 1/2 instead. And then we can add the 1, which is equal to y. So now we can actually see what our vertical or horizontal stretch is. This is our horizontal stretch. This is our horizontal translation. And this is our vertical translation. So those are just little things that we can do to actually see those. And that's it. So that's our final answer. So 3 to the power of 1/2 in brackets, x minus 8, close your brackets, plus 1 on the same level as the 3 equals y. Okay, so that is your lesson. So that is lesson 8.2, transformations. So it's stuff that we've done before, but just kind of applying it in the logarithmic or exponential form.